So again, it's my privilege to welcome you all here to Ben Ackerman's dissertation defense. Ben arrived here with us in 2015. He was an undergrad over on the Homewood campus here, public health studies major and applied math and statistics minor. I first met Ben about 4 years ago, I think-ish, when he came up after a course that it's all coming around full circle. Danny was teaching a course on autism, and then I guest lectured, and Ben came up after and said, "Oh, I want to hear more about your work," and all moved from there. And you'll hear today about his dissertation work. One of the things that has really struck me about Ben is his balancing of sort of really high-quality statistical work with a strong desire to do social good, and that was evidenced by time he spent in Chicago in the Data Science for Social Good program. The letter for that was like the easiest recommendation letter I've ever written because it was such a good fit. He's also collaborated with a number of groups in the school. You'll see a tiny bit on that. And I want to I might say more later, but I want to highlight Ben's communication skills, which are, I think, excellent and really help translate statistical methods. No pressure. And then also his ability to form communities. And sort of I view a large part of the success in what we do as part of our ability to build communities and build collaborations. And Ben really excels at that, including receiving a special departmental recognition award sort of in recognition of that. And this is on top of all of his dissertation work. And this is sort of informal, including things like biostat tea time, which I think many people in the room have benefited from. So Ben has been super busy with all sorts of things, both inside and outside of sort of statistical work, and I will turn it over to him so he can tell us about that work itself. Thank you.
Thank you, Liz, for the kind introduction. I think the only word to describe how I feel right now is verklempt. So, wow. I'll save the tears for later. But thank you all so much for coming. It really means a lot to me to have all of you here. And for those of you watching in the spillover room on YouTube Live, thank you for also being here virtually and in person. So today I will be sharing with you about my dissertation work that I've done under the advising of Liz Stewart. So before I go into the statistical work, I want to give a little bit of background of sort of how I came to this program and what I've hoped to achieve through this PhD. So I came to this department from an undergraduate program in public health studies, and that has really motivated me to join this department and engage in research that aims to use, build, and disseminate quantitative methods with the goal of promoting social good and improving population health. And so I like to think of myself as sitting in the center of this cheesy Venn diagram of data science, public health, and statistical methods. So briefly, I had the privilege to work with a team of data scientists at the University of Chicago through this Data Science for Social Good Fellowship, where we partnered with a nonprofit network of community health centers to build a predictive risk model for type 2 diabetes. And the goal was to overcome some disparities in type 2 diabetes screenings. I also have used R and Shiny apps to raise awareness and for advocacy. There was a tax bill that was floating around that would have harmed a lot of graduate students financially and disproportionately students in STEM fields. So I've used data science to promote social change and social good in these ways. Luckily, that bill was struck down. I've worked on a number of different applied health projects, some of which I'll talk about today, but in addition to my dissertation work, I've had the joy to work with some folks here at Hopkins on some projects related to LGBT health, mental health, autism spectrum disorders, and a couple of these other areas that I'll talk about in a second. And then I guess the bulk of the work in my time here, my dissertation work, has been centered around statistical methods with issues related to clinical trials. And so I've been really interested in ways we can use outside data sources and leverage information from outside sources to better improve the inferences we draw from trials. And so I'll be talking about this concept of transportability throughout this talk. And in addition to the methods work that I've done, I've also worked on developing some software and an R package to really make sure that these methods are accessible for applied researchers who will use them out in practice. So I want to give a little bit of motivation of two clinical trials that I'll be using as examples throughout this talk, and also use this to sort of set up the concept of transportability. So the first trial that I'm going to be talking about is a trial related to substance use disorder treatment. And with this trial, we're particularly concerned that the sample is not representative of some broader population we care about, and that there might be some subgroups of folks for whom this treatment works better than others. And so we'll be asking, how can we generalize these findings to a population of US adults seeking treatment for substance use disorders. The other trial after that I'll be talking about is a lifestyle intervention trial aimed to reduce sodium intake. And the problem we're concerned about with this trial is that we have self-reported outcomes, and we're concerned that they might be measured with some error. And so we want to know if we can correct for that error using some outside data. So for the first part, I'm going to be using an external data source to represent the target population that we're interested in. In the second case, I'll be using an external data source that's a validation study that we can use to model the measurement error structure to correct that in the trial. And so the way I like to think of transportability with these cases, on the left-hand side, we're going to be transporting the effect from the trial to our external data or population. And then on the right, we're going to be transporting the effect from our outside data source with the measurement error correction to improve inferences within our trial. So first, again, I'll be talking about this work related to external validity and generalizability. So randomized trials are considered the gold standard for estimating causal effects, so to see how well an intervention or some drug works. And this is because we have randomization of treatment assignment, so we can unbiasedly estimate the sample average treatment effect, or the SATE. And trials are particularly used often in policy formation and in making population-level decisions. So evidence from trials are highly regarded when stakeholders are trying to decide what effective treatments to make available to their populations. However, a lot of these policy and population-level questions require us to estimate the population average treatment effect, or the PATE, which may be different from the SATE. And so there's growing concern that findings from clinical trials, particularly if we have a trial that's not representative of our target population, that the findings may not hold when generalized to a broader target population. So we can imagine if we recruit a bunch of Hopkins grad students to participate in a trial, and we see some promising effect of some drug, we might not think that that same effect would hold if we made that widely available to everyone in the US. And so, more formally, if we have this poor external validity in a trial, our SATE will not equal our PATE. And this will happen if we have a variable that moderates the treatment effect that differs in distribution between our trial and our target population. So for example, if we have a trial that's 80% male, 20% female, and we see that some drug works really well in this study population on average, it would be hard to imagine that that effect will hold and generalize to a US population that's maybe closer to 50-50. And so there are a couple of ways we can address generalizability. We can tackle this issue through smarter trial study design and recruit representative samples to reflect the target population we're interested in. However, in a lot of medical trials, this is infeasible for time and financial constraints and strict exclusion criteria. And so today I'm going to be focusing on some post-hoc statistical methods where once a trial is already done, we can do some adjustments to better estimate a population effect from this trial that has this issue. And so I'm now going to give a high-level visual overview of sort of how these methods work and how we can do this using outside data. So say we have a trial, this square in purple, that's nested. It has participants are from this broader target population that we care about. But we're concerned that our findings will not generalize to that target population. So what we can do is find some non-experimental study data that we think represents the target population, and we can transport the effects that we see in the trial to that population. And so how can we do that? There are sort of two different classes of methods that we can use to do this. On the right, one approach we can use is to model the outcome in our trial as a flexible function of observed covariates, and then use our external population data to predict the effects under treatment and control in our population. And then we can also take a weighting approach that's similar to propensity score weighting, where we can weight our trial sample to better resemble this study data, this non-experimental study sample, based on some baseline characteristics. And so today I'm going to be focusing on these weighting methods, but I just want to note that these more flexible machine learning methods for modeling the outcome are also available. And so I want to give a little bit of notation. So throughout this section, I'll be using the variable s to denote sample membership. So s equals 1 will denote a participant is in the trial. S equals 2 will denote that they're in the population data set. I'm going to use y of a to denote potential outcome y under treatment a equals little a. So little a is 1 if it's treatment, 0 if control. And then I'm going to define the estimand of the SATE, the sample average treatment effect, as the expected difference in potential outcomes y, conditional on being in the trial sample. So if we just look at the effect among the trial participants. However, what we're really interested in is the population average treatment effect, or the PATE, which is the expected difference in outcomes in the population, so not conditional on this S. And so I'll also use X to denote a set of pretreatment covariates throughout. And so now I'm going to walk through step by step how we can construct these weights that I referred to, and then transport our estimate from our trial sample to our non-experimental study data and thereby to our target population. So the first step in implementing these methods are to find a full data set on your target population. And I'll come back to this in a second. This is often easier said than done, but finding that external data is sort of step one. From there, we need to stack and harmonize our two data sets. And so what we have in the end is a data set where we have some indicator variable for sample membership. We retain the outcome and the treatment assignment in the trial data. We don't have those observed in the population data, but that's fine because we're just using that to look at the covariate distributions. And then we collapse across categories and harmonize however many common covariates we have across the two. So we prepare the data, and then we fit a model of sample membership. So similar to propensity scores where we model treatment assignment, here we're modeling whether or not someone is in the trial or this population data sample. And so one way we can do so is fit a logistic regression model with this binary S as our outcome and our covariates as our predictors. And we can use other sophisticated methods like random forest, GBM. Throughout this talk, in my data example, I'll be using GBM. It's just been shown to perform a little better, but I just wanted to allude a few methods, but you can fit a logistic regression model here as well. Oh, sorry, it's a boosting algorithm. Generally boosting. Sorry, a lot of acronyms in this talk, so apologize. So from this model, we can predict for every participant or every member the probability of participating in the trial based on their X covariates. And then we can use those predicted probabilities to construct weights. So we're going to weight our trial participant by the inverse odds of this predicted probability. We're going to set a weight of 0 for our population data. And again, that's just because we're weighting the trial data and then estimating the effect in that weighted sample. And so then we can estimate our PATE as some weighted mean difference of outcomes under treatment and control conditions. I also want to note that this is somewhat easy to implement in R, and there's a link to the R package that I've been working on developing. So with every method, there come assumptions, and so I want to discuss some of the assumptions that we have to make to use these methods now. Some of these are fairly analogous to propensity score assumptions that we have to make. First, we have to assume that all members of our target population have a non-zero probability of being selected in the trial. So similarly, we have to also assume that the range of the covariates and effect modifiers in our target population are covered by the respective ranges in the trial. So this is to say, if we have a trial of folks between the ages of 20 and 40, we can't generalize those findings to people who are 60 and above because we just don't observe them in our trial. We also have to assume that treatment assignment is independent of sample selection, as well as the potential outcomes given pretreatment covariates. And then this last assumption, we have to assume that there are no unmeasured variables or modifiers that are associated with how you're sampled into the trial or associated with treatment effect. And this oftentimes in practice is kind of a grand assumption to make, and so there's been some great work by some folks in this room on sensitivity analyses for how to handle unmeasured modifiers. And then there's actually a fifth assumption that we sort of implicitly have to make that has been much more under-discussed in the literature, which is that the data we find on our target population have to be a simple random sample of the true target population. So we have to assume that the data we find really do represent the population we care about. Either that or that this data set is the complete finite population of interest. And so this raises some problems. And so going back to the first step of these methods, you may be wondering, where do we find data on our population of interest? So in practice, this can be very challenging. We might find that our target population of interest is pretty specific, and maybe we find data sets that are somewhat related to that population, but don't really accurately describe the population we care about. More commonly, we might find a data set that's publicly available that has a limited set of covariates that we can adjust for. So there might be important modifiers of treatment effect in our trial that some publicly available data set just didn't measure, and that would raise issues around unmeasured treatment effect modifiers. And so one increasingly common source of data that are being more and more recommended to use are large government health surveys. So surveys like NHANES, NHIS, even more acronyms, I apologize. But these are large, complex surveys that are used frequently in a lot of epidemiological studies that are publicly available. And these are promising sources of population data for a number of reasons. One, they collect a pretty wide range of variables, so there's a better chance that there are enough things we would want to adjust for in these data sets. And they also span a number of different types of populations of interest. So we can hope that there are more populations described in these data, and this can hopefully circumvent some of the issues of not being able to find adequate population data. As promising as these data sources are for being target population data, there is a slight issue in using them in that these surveys are collected using complex survey design, and they're representative of their broader target populations only by the use of what are called survey weights. So these surveys use probability sampling and systematically over or undersample certain groups, and then have some known mechanism by which those study participants are related back to the true target population that that study is interested in. And so the assumption, this last assumption we make of our population data being a simple random sample would be violated if we use one of these survey data sets for generalizations. And so, for example, if we use the NHANES survey sample as our population, it would be as if we transport our effects from our trial to the raw NHANES survey sample demographics, which may or may not reflect the target population that NHANES is trying to represent. And so this poses another issue and raises the question of how can we generalize to the true population we care about using this type of population data. And so I want to formalize a little more why this is an issue. And so this Colin-Stewart paper expanded upon the definition of our estimand, the PATE, to show that the PATE is equal to the observed effect in our trial. It's equal to the observed effect in our trial if we're able to weight that somehow by the mechanism by which the trial participants were sampled. So we can estimate our PATE if we have our trial sample and if we can relate that back to the target population. So if we know this inverse probability of the trial participants being selected, we can use those easily. However, the issue is that these probabilities are not directly known. So going back to this diagram, that would correspond to this arrow here, And that sort of motivates why we're using this external data in the first place, because we don't know how these participants were sampled, and so we can't ever actually estimate this quantity. And so one thing we showed was that we can decompose this quantity into two different things that we either do know or can estimate. So we see that it is a product of the transportability weights. So if we fit the model and get our weights as I described before, it would be a product of those weights and the survey's known survey weights. And so if our population data really are a simple random sample, then this term on the right will go away, and that sort of motivates why if we transport using a simple random sample, using these inverse odds weights are sufficient for getting to the target population we care about. But if not, and if we use a population data source and we omit these weights, then we may have some problems. And so, yes, so if we estimate our effect using the existing generalization methods and we don't account for these survey weights, then we may have a biased estimate of our pate. And so this raises the question of how can we generalize to the correct population using population survey data. And so this is where the methods development comes into play. So we propose that in the process of fitting this model and obtaining our transportability weights, we propose fitting a weighted sample membership model where we're going to use the survey weights when we're fitting that model. And so I'll show this process again and show you where this fits in with it. So again, we find our population survey data, we stack and harmonize our data, where now we're also going to retain the survey weights from our population survey, and we're going to set the weights equal to 1 for our trial, because we don't have any known selection weight there. And then the rest is the same as before. And so then we go to fit our model of sample membership, where we're going to use our sample membership variable as our outcome, regressed on our covariates. But when we do so, we're going to weight the trial participants by 1, and we're going to use the survey weights here to weight the survey participants. And so what this is doing, essentially, is say someone in the survey data has a weight of 500. That's to say that there are 500 people in the target population who look like this person. And so when we use those survey weights, it's as if we're creating a pseudo-population, and we're then comparing the X distributions between our trial and the true target population that that survey was sampled from, as opposed to just the raw survey sample characteristics. So we use the weights here, and then we go about predicting the probability of trial participation, construct our weights again, and then we estimate our pate here as the weighted mean difference. And so now I'm going to talk about an application of these methods to the trial we're interested in that relates to substance use disorder treatment. So this project, we're using a trial that comes from the National Institute of Drug Abuse. They have a publicly available repository of a bunch of clinical trials that make it great to do some secondary analyses. And so this one trial in particular we're going to use randomized 505 individuals who were all in outpatient treatment for substance use disorders, and they were randomized to one of two groups. Either they received their treatment as usual, and they just continued their outpatient treatment, or they supplemented their outpatient treatment with this therapeutic education system, TESS. And TESS is a web-based intervention that has skill-building modules, and they have incentives to promote abstinence from substances and alcohol. And so the outcome of interest here is abstinence from substances and alcohol upon study completion. And so I also want to note that this trial originally found TESS to be effective in improving abstinence compared to treatment as usual among the study participants. So this trial found some promising findings that this web-based intervention could help folks who are in treatment for substance use disorders to promote abstinence from drugs and alcohol. And so we want to know whether or not these findings will generalize if we apply them to all adults in the US seeking treatment for substance use disorders. And so I want to give you a quick snapshot of what the trial participants look like. About 40% are female. The age distribution is fairly evenly spread. But one thing I want to call your attention to is the prevalence of prior intravenous drug use. So we found in some secondary analyses that there was some treatment effect heterogeneity with respect to whether or not folks reported prior intravenous drug use. And the prevalence in this trial sample is around 14%, which may be a bit high when we go to compare to our target population of interest. And so for our target population, we're going to be using data from the National Survey on Drug Use and Health, which is an annual cross-sectional survey that has the goal of measuring substance use disorder problems and mental health outcomes in the United States. So the survey has a target population of civilian, non-institutionalized folks in the US who are aged 12 and older. For the purpose of this example, we're going to limit that population to folks 18 and up who had reported prior substance use in the past 30 days and were currently seeking outpatient treatment. And so this particular survey also systematically oversamples individuals who are 26 and up so that they can better estimate drug use and mental health issues in the US. And so this is a survey where we're particularly concerned that the survey weights matter, and whether or not we use the survey weights, we may be generalizing to the population we care about or to some other arbitrary population that may not be of interest to us here. And so if we compare our trial to the raw survey sample, we see that there are a couple of differences between the two samples, namely age and also, as suspected, the prevalence of prior IV drug use is around 5%, so it's much lower. And so this raises concern that our findings may not generalize to this population. However, this is the unweighted survey. What we really care about is the target population, so the weighted survey. And so when we compare the weighted survey to the unweighted survey, we start to see some pretty big differences, which suggests that, again, if we leave out the weights or use the weights, it's as if we're generalizing to two different populations. And I also want to note that we ran some simulation studies to show that, in fact, if you omit the survey weights, you'll get a pretty biased estimate, and it might in part be because it's as if you're using a different target population of interest. And so here, when we use the survey weights, the age distribution changes pretty dramatically, so does marital status, and we see some slight changes in prior IV drug use and past substance use treatment as well. So now I'm going to show some results where I'm going to compare the naive trial estimate, so what happens if we just estimate the effect in our trial, what happens if we transport to the raw survey sample, and what happens if we transport to the population using the survey weights. So first, we replicated the original study findings. So the y-axis is the odds ratio of substance abstinence, and this is our unweighted trial estimate, which had an odds ratio of around 1.6. Confidence interval did not cover 1, so this would suggest that TESS was effective in promoting abstinence in the trial sample. When we transport to the raw NISDA survey sample, we see a couple of things. One, we see that the point estimate of our odds ratio drops below 1. We also see that the confidence interval width increases, in part because we're using weighting, so that will just naturally increase the confidence interval. And we also see that that covers 1 to suggest that this intervention is perhaps not effective in promoting, or we don't have enough evidence to suggest that it is effective in our population. But again, this is sort of hard to reason because this isn't the target population that we care about, and we don't actually really know what this population is. What we care about is the survey-weighted population, and so when we use the survey weights, we see that the estimate, or point estimate, better reflects what we originally saw in the trial. However, our confidence band still covers the null value, but you can imagine that a decision maker or a stakeholder might draw some slightly different conclusions about the effectiveness of this intervention, whether they see what's on the right or what's on the middle. And so to just illustrate that whether or not we use the survey weights does make a difference for which population we actually generalize to, and sort of a caution when using this type of data where we're solving one problem of data availability, we sort of create this other methods issue where it's important for us to incorporate the survey weights here. And so up until now, I'm checking time, I've talked about one way to use propensity score type weighting methods where we can transport findings from a trial to an external data source, and some practical issues that come up when we do that, and some methods fixes to overcome those issues. Now I'm going to talk about the other use case in my dissertation work where we're going to similarly use these propensity score type weighting methods, but we're going to transport an effect from our external data to our trial of interest. So, and this work is motivated by issues that come up in lifestyle intervention trials. And lifestyle intervention trials are particularly important when we're trying to demonstrate the effectiveness of some lifestyle interventions, which are like dietary and exercise interventions and recommendations. We want to evaluate the effectiveness of those on health outcomes. Such trials often depend on collecting self-reported measures, such as dietary recall, and these measures are used in a lot of different ways, both as exposures of interest or covariates, but also sometimes as primary outcomes of interest in a trial. And self-reported measures are often collected because true measures, like biomarkers or urinary samples, blood work, can be costly and cumbersome to collect for all study participants. So while the self-reported measures may be more convenient to collect, they are prone to measurement error. So I can tell you that I didn't eat a pint of ice cream last night, but my blood work might tell you something different. And so fortunately there are methods to correct for this type of measurement error where folks over-report their true behaviors. And we can use external validation studies, which are studies that measure both the self-report, so what I say, and also some underlying biomarker, so what is suggested through my blood work or urine sample, which we'll assume to be the truth. However, most of the previous work in measurement error and using external validation studies has focused on measurement error in exposures, and less attention has been paid to measurement error in a trial outcome. And so we're concerned here, and I'll go through this throughout this part, that correction using validation studies may not accurately apply to a trial, and so we're going to propose some methods and some use of these propensity score type methods to better account for this. So I'm going to use some notation from the measurement error literature here, where now I'm going to use Z of A to denote the true potential outcome under treatment A. So Z is going to be like our biomarker, and Y of A is going to be the potential outcome Z measured with error. So using measurement error notation, we're going to say Y is equal to Z plus some error term that we're going to assume is normally distributed with some mean and variance parameter. And I'm going to use S again to denote sample membership, because we're going to still be talking about a trial and some external data. But here I'm going to use RCT to denote the trial and V to denote our external validation study. And so in the last section, we were interested in estimating the PATE, or the population effect. Here in this section, we're just going to focus on estimating the SATE, or the sample average treatment effect, which again we'll denote as the expected difference in potential outcomes of the true, not measured with error outcome in the study sample, in the intervention trial. And so in our trial, we often don't observe Z, so we don't observe the truth, but we do observe Y, the outcome with error. And so if we estimate our SATE using the outcome measured with error instead of Z, this might lead to a biased treatment effect estimate, where this bias is going to depend on sort of the means of the error under treatment and control. Yes, so this mu term is going to be, in the slide before, this error mean of our measurement error under treatment and control. And so now I'm going to use a superscript to denote that the parameters we care about here are the error means under treatment and control in our trial. And so, as a reminder, in our intervention study, in our trial, we'll observe the mismeasured outcomes under treatment and control and our covariates X. And in order to correct for this measurement error, there's this Sadiq et al. Paper that proposes using an external data source in the following way. So we can find some validation study that again will measure the mismeasured outcome Y and some true measure, some biomarker Z, which we're going to assume are under control conditions only. So we don't observe anything under treatment conditions, and we still have our covariates. So Sadiq et al. Suggests using this validation study to estimate the error under control conditions using the validation sample, and then assuming that that holds and transports directly to the trial of interest. And then since we can only estimate the error under control, we can do some sensitivity analyses to see how much more bias there is in the treatment group. However, we're concerned that this transportability assumption may not hold, and will that introduce further biases or further problems? And how can we use these weighting methods to account for them? So this transportability assumption more formally is stating that the error structures under treatment and control are the same whether we're in the validation sample or the intervention study. So when we assume transportability, we're assuming that the error means in our validation sample are what they would be in the trial. And this may not be a viable assumption if the studies differ greatly by a factor that impacts how much error there is. So sort of similar to before, say if BMI, if there are folks in the trial, or if there are folks who higher BMI, they over or under report certain self-reports at higher rates than the other group, and our intervention study has on average higher BMI than our trial, or than our validation sample, then we might expect that this transportability might not hold. So if this is violated, then our estimate of this error in our validation sample may be biased for what it truly is in our trial. And so similar again to the conditions under which transportability doesn't hold for external validity, one thing we did was we showed that this transportability will be violated for these reasons again. And so if both of these conditions hold, where the error is differential with respect to some covariate, and that covariate differs between our trial and our validation sample, then we'll have a biased estimate. And so here again, we propose using the same propensity score type weights, where we're going to weight our validation sample to look more like our trial to get a better estimate of how much measurement error there is under control conditions. So again, this is similar to propensity score weights and the transportability weights that I described in the first part. And so again, we can go step by step. We fit our sample membership model conditional on our pre-treatment covariates, where we have whether or not you're in the trial or the validation sample as our outcome and our predictors of sample membership. And then we can construct our weights using those predicted probabilities, where here we're going to weight the validation sample by the odds of trial participation. And then we can obtain a weighted estimate of our error mean, just as we did before. And so with this project, we also looked at an issue of model specification of the sample membership model. So say we use logistic regression. If we were to fit the exact true model that relates the sample membership to our covariates, then we can get an unbiased estimate of this error mean. However, if this model is misspecified, which it almost always is, because no models are ever correct, then we think we can still do a better job than no weighting, but it still may be slightly biased. And so in order to look at how this impacts our ability to get an unbiased estimate, we ran a simulation study. And so I'll go through this very briefly, or I'll skip it. I'm getting the signal. It's not that interesting. But basically, we showed that even if you use weighting and you misspecify your model, you still do much better than if you do net weighting at all. So, thank you. So we applied this to a trial and a validation sample. The trial we're interested in is called Premier, which was a multi-arm lifestyle intervention aiming to reduce sodium intake. And so this trial had a self-reported outcome of dietary sodium intake, and we're actually assuming that there is no urinary biomarker available, in truth, this trial does have the biomarker, so we can actually use that to evaluate how well we're doing, but we're going to pretend it doesn't exist for now. And then we're going to use a validation sample called open that has both self-reported sodium intake and a 24-hour sodium urinary biomarker. And we're going to assume that the conditions of open are equivalent to the control conditions of our trial of interest. And so if we compare open and Premier, we see that our trial, so Premier is the trial on the right, we see that there are fewer males in the trial, the BMI in the trial on average is higher, there is some differences on race and education, and in some secondary analyses we also found that the measurement error of sodium intake in our validation sample was in fact differential by different groups depending on sex, race, and education. So the transportability assumption here is violated, and so we're going to use these weighting methods to see if we can get a better estimate of this error mean in open and apply that to Premier. And so we fit a sample membership model accounting for age, sex, race, education, and BMI here. And so I'll just show the results briefly and then move on. So on the left, we have our estimates. So the top row is our unweighted. So what happens if we just use open as is to estimate this error mean under control conditions? In the middle, we have the truth. So I said we do actually have this biomarker in the trial. And so we see that the unweighted estimate has a bias of around 0.077. When we use this weighting approach and we weight open our validation sample to look more like our trial, we obtain an estimate of that error mean that has a reduced absolute bias. So it's not zero, and this is presumably because of maybe some model misspecification or some other issues I'd be happy to talk about in the questions if you have them. But this weighting here we demonstrated to be effective in getting a smaller absolute bias than had we done no weighting at all. So to conclude, today I talked about some issues in clinical trials where, again, trials are considered this gold standard for estimating causal effects, yet they still may have flaws. So if a trial has issues of being representative of a target population and there's some subgroup effects, then there might be weakened external validity. If there's outcome measurement error in our trial, there might be weakened internal validity. Today I talked about two different ways in which we can supplement trials with external data in order to try to address these problems, and that if we fail to address, if we fail to use these data properly and we don't assess how compatible they are with the trial of interest, this could lead to further problems, and today I talked about a few methods fixes to how we can overcome those problems in practice. And so yes, this methods work aims to improve how we can use these data. Yes, this is just another summary of that, so I'll skip this also in the interest of time. Some future work, I think it would be interesting to try to tackle both internal and external validity together. Today I talked about these issues separate, and then I also hope to keep working to translate this method's development into practice and build tools for people to use to, again, get back to my overall goal of promoting population health and social good using and building new statistical methods. So with that, I want to put up some references from the first part, some references to the second part. You can send these slides out if you would like to read some of these. These are some related resources that I've worked on throughout my PhD. And now is the part where I don't cry, but I have a lot of people to thank. So that sort of ends the talk part. I just want to go through and thank some people who have been instrumental in this work and my graduate school career. So first, I, of course, need to thank my PhD advisor, Liz Stewart. Liz, I hope you don't mind that I use these pictures, but I think these two pictures sort of nicely sum up how I've perceived our advising relationship. On one hand, on the left, you've provided me with countless opportunities to grow and learn as a researcher, as a writer, and as a communicator. And on the right, you've also shown me how to maintain work-life balance and be productive while making sure not to sacrifice or undervalue my personal life and my well-being. So this photo is from a dance floor, I think at the Hopkins Biostat Centennial Party. But if there's a dance floor at a conference, Liz is always there, being the coolest advisor around and trying to drag me onto the dance floor. So thank you. But in all seriousness, you've really helped me find not only my voice, but my confidence as an applied statistician. And you've taught me the importance in seeking statistical questions that are embedded in impactful health-related problems. And you've inspired me and been a great role model all of this time. So I can't thank you enough for all that you've done for me, and I'm really going to miss working with you, but I can't wait to stay in touch as colleagues and maybe even, dare I say, as friends, wherever I end up. And so I could list more and more reasons why it's been so excellent working with Liz, but I also really want to acknowledge some of the collaborators through what is now called the Stewart Lab. And so a lot of you are here in this room. Thank you so much for pushing me to be more rigorous and thorough in my work. It's been a real joy getting to collaborate with you all and share ideas with you and give feedback. And so yes, this is a growing list of folks past and present who have all made a difference in my graduate school education here. I'm not going to list all of these people, but I really want to thank my thesis committee, Danny, Katie, and Betsy, in addition to Scott and Joanne, and some folks who are on my other doctoral exam committees, Ramin and John. It's been really awesome getting to work with you and get your feedback, and for you to keep me on track, and for all of your advice, feedback, and your steady encouragement. Among the people from the biostatistics department, I especially want to thank Karen, our chair. I feel very lucky to have been in this department with you as our chair. You've led with so much compassion, and you've been incredibly generous to me with your time and your support. And I especially want to thank you for being a fierce, dedicated chair for the well-being and success of all students in this department. You always talk about how special this department is, and I just hope you know that you contribute so much to what makes the culture of this department special. These first few years of the program were really challenging, and thanks to support from people like you and Brian Caffo and Scott, who were my advisors and program coordinators or program leaders at the time, you really made me feel like I belonged here, and your reassurance made a big difference to me, so thank you. I got to work with a lot of great collaborators. Thank you all. Helen, I think it's wonderful that you're here. Thank you so much for all of your support over the last several years. Kate Bradford, thank you for showing me that I could do all of this in just 3 minutes. It's probably would have been a useful skill to use today. I want to thank all of my friends from Hopkins and Hopkins Biostat. You've really made this experience a lot of fun and enjoyable. Oh my gosh. There's another slide. But really, you've shown that, you know, we work hard, but we're there for each other. I gotta thank my boys, Jacob and Lamar and Matt, for, you know, we've stuck together all 5 years, and it's been really great having you, and thank you so much for all of your support. I thanked my Hopkins friends. I must thank my non-Hopkins friends who've made Baltimore feel like home. Thank you, Sarah. Thank you, Rachel. Thanks for supporting me and for distracting me from the stress of grad school, for always cheering me on and eating lots of ice cream and Johnny Red's pizza with me. The friendships and communities that we've built here in Baltimore have been really special to me, and so I feel really lucky to have you in my life and here today. To thank my boyfriend Michael. I'm going to lose it. Thank you for being a voice of reason, a calming presence, and someone I can always depend on. I love you very much. And now I'm really I have to thank my family who are here today. You really know that more than anyone that this hasn't been easy for me at all. And thank you for always being good. Thank you for never giving up on me and comforting me at some of my lowest moments and cheering me on in some of my proudest moments. And I'll also thank my grandma, who always knew this day would come, even when I couldn't see that it was going to come. I wish she were here to celebrate, but I know she'd be really proud of me. And then I promised Danny this is the end. I need to thank all of the great dogs that have comforted me in grad school. I've always wanted a dog my whole life. I've never had one. So I want to thank all of these good boys and girls for letting me love them and making me smile. Many of their humans are in this room. Thank you for giving me time with your dogs. But in particular, I need to thank two special dogs who have been there long term. So I would be remiss if I didn't thank Charlie, the geriatric corgi who now lives in Cleveland, and Michael's dog Benny, of whom there is no name relation. But just 5 minutes with any of these dogs would cure the worst days I've ever had. So with that, I want to thank you. If you don't have time for questions, you can contact me. Only a few tears.
Questions?
Oh.
It seems to me that everything is 45 is represented. How do you define that?
Yeah. It's a good question. I would define representativeness as having an equal distribution of the folks in our population, a proportional count of them in our study sample. So if there were, I guess, 20% of some demographic group in our population and only 10% of our study sample had members from that group, I would say that there might be a representativeness issue.
Yeah, and also,
You asked me that a few years ago, and I was ready.
Also coincides with something that was very popular in the 70s and 80s, like balance. Did you notice anything?
In terminology, yes, past that. But I agree, I think. An approach to sampling sampling participants that are strategically representative in that way is important. And today I didn't really talk about any methods for doing so. I also want to note in the education world, in particular, there's a much more robust literature on recruiting schools such that their participants are reflective of some target population of interest for SCTs. Marta. Mm-hmm. Yeah. Yeah, that's a good question. And I think you're right, in practice, using these methods, you might have a covariate that's categorized or asked in one way in a trial, and then asked maybe on a different time span or with different categories in the population. I think it also raises an interesting question of measurement error, and again, where it could be advantageous to look at these two problems together. But yeah, I guess in practice, I've tried to use them and hope that sort of the measurement error is not wildly impactful, but it would lead to some interesting methods questions. Yeah. Mm-hmm. Mm-hmm. Mm.
Something that is strong evidence in favor of
Mhm. Yeah, that's interesting. I guess that also raises some thoughts and question around if there is some underlying heterogeneity, why are we not trying to better estimate subgroup effects and report on them? And so I think the question of interest and the population of interest is important to consider a priori, and certainly for some of the policy questions, we might still be interested if we make something available on average, how well will it work? But I totally agree with you. Rachel. Or, yeah. Yeah. It's a good question. Well, I guess on one hand, this is your question. You're gonna. Should I hold it? Should I now? All right. I think there could be a couple. There, academic researchers who are interested in policy evaluation, or there could be stakeholders who I think, in seeing evidence from trials, would benefit from an analyst who is helping them be able to implement some of these methods and provide a better population estimate.
One more.
If there's a measurement error that I think like more completely applied if you're using there is a strong differential measurement error on your first trial. But the way we presented it with the external validation is probably only going to have measurement error for a non-exposed, or at least only one non-exposed. So is there a way to address the measurement error, the differential across the exposure levels, or would you just need an additional validation?
Yeah, that's a great question. And so yes, I guess I sort of glossed over it, but this whole issue really comes up if the error is differential with respect to the exposure treatment. And so I think often why this issue doesn't get addressed is that people assume those errors will cancel, or that the error in the treatment group and the control group are going to be the same, and we won't mitigate this bias. I think if we wanted to correct for error, I think it's tricky. If we wanted to correct for error in the treatment group, it might require some external study that has that condition. But sort of thinking through, if we had an external study that had both measures on treatment and control, it would be as if it was its own trial, and we would maybe not need an external data source, but could just use the true outcomes and circumvent that. That's a good question.
All right, well, let's thank you again. Remember to say hi to all your overflow folks.
Thank you.
You can go hang out with them then. Yes.
I can.
So you guys out.